Okay, so we've been spending quite a bit of time on Qr factorization, and today we're just going to spend a little bit more, and then we'll be able to move on from there. But Qr factorization is going to be coming up fairly often for the rest of the semester. Okay. All right. So some of you may have seen Gram-Schmidt orthogonalization in an ordinary linear algebra class, because you'd be given a problem where you'd be given a set of vectors, and the problem was to obtain an orthogonal set of vectors from the given ones. So basically making them orthogonal, really orthonormal. So that's what we're going to apply here, where the original vectors you're given are the columns of a matrix A. So you're orthogonalizing those columns. And the orthogonal columns will give you the Q in a Qr factorization, and then the linear combination of those columns to give you back A would be the R. And it's probably of all the different methods of computing a Qr factorization, Gram-Schmidt is probably the easiest to understand. But numerically, it is also undisputably the worst, which I'll get into toward the end. Okay, so get into the details now. All right. Now, when I first wrote out the Qr factorization at the very beginning of a chapter, A is m by n, or m is greater or equal to n. Q is a square matrix, so m by m. And then R is this matrix that has R1 up top and 0 down below, but that has the same size as A. Now, the two methods that we've seen so far for computing a Qr factorization, givens, rotations, household reflections, will give you this full Qr factorization. You get all of Q, you get all of R. But Gram-Schmidt orthogonalization is not intended for that. It's a smaller version of the Qr factorization that we have here, where we're after just Q1 and R1, because if you were to multiply out these two matrices, it'd be Q1 R1 plus Q2 times 0. So Q2 does not actually play any part in making up A. Q1 is enough. So it's these two smaller pieces that we'll be going after. So, so when we carry out the multiplication, A is not only equal to QR, it's also equal to Q1 R1, just because there's no contribution from Q2. Also, A is assumed to have full column rank, linearly independent columns. The rank of A is n. So it turns out that the subspace spanned by the columns of A is the same as the column space of Q1, which makes sense because what this factorization is saying is that every column of A is a linear combination of the columns of Q1, and the elements of R1 give you the coefficients in that linear combination. Now, a column space of a matrix is a set of all linear combinations of the columns. So from this factorization, you can see that the space spanned by the columns of these two matrices would be the same, just because they're linear combinations of one another. In fact, we can actually make a stronger statement than that. That if I take the first k columns of A and the first k columns of Q, or Q1, those spaces are the same. So all linear combinations of a first k columns gives you the same subspace as all linear combinations of a first k columns of Q1 or Q equivalently. And just to make sure the notation is clear, these are the columns of A. So if this is a column partition, and we have the same kind of column partition for Q. Okay. All right. So what this is saying is that the first k columns of A can all be described as linear combinations of the first k columns of Q. So what we're going to compute here is this QR factorization instead of the original. So what that's referred to is called the thin QR factorization, also the economy size QR factorization. And the thing is, keep in mind why we want the QR factorization in the first place. It's to solve full rank least squares problems. And to do that, this factorization is enough. The reason why is if we have Q1 and R1, then we compute Q1 transpose B, and then we solve this upper triangular system of equations where the matrix is just R1. So that'll be enough to get us the solution X that minimizes this. Oh yeah, quick comment about QR factorization and Matlab. Actually, I need to see if this has changed based on different versions. Yes, okay. All right, so if you do A, QR is equal to QR of A. So this is the simplest usage of MATLAB's QR function. Gives the factors QR as the output. That gives a full size factorization A equals QR. Or this cube, a full cube, that's a M by M square matrix. Now, if that's not what you want, if you want the economy size, Q1, R1, you can do same usage, except you need a second argument of 0. Okay, so that gives us Q1, R1. Okay, so it's important to keep in mind which QR factorization do you want for a particular purpose before using this QR function. Okay. So now we'll look at this algorithm for getting the economy size factorization. That's classical Gram-Schmidt. So this is the one that they teach in ordinary linear algebra courses. It's a terrible method, but at least it's okay as a starting point, and then it can be improved. That's the sort of thing that would only be talked about like in a numerical analysis class, like this one. Okay. All right, so here's the thin QR factorization that has all the columns of A equal all the columns of Q1. So notice in Q, we go up to from Q1 up to QM, but in Q1, we only go up to Qn. So we only need that many columns. And then times this our triangular matrix. So these are all the things that we want to compute. So what if we look at the first column of this matrix equation? Well, on the left side, we just have A1, the first column of A. And then the first column of the right-hand side, you'd be taking all these columns of Q1 times all the entries in the first column of R1. So you have Q1, R11, plus Q2, R21, etc. But in the first column, R11 is the only non-zero entry. So really it's just going to be Q1, R11. This is all we get because of the upper triangularity of this matrix. So in that case, it's very easy to get the process started. That we go ahead and okay. Actually, yeah, that shoot. Another mistake, or at least something unclear in the book. What I should have here is R11, just to make sure that this works, that this is equivalent to this. So what we do is we can compute R11 equal to plus or minus the 2 norm of the first column of A. Now we're going to choose a plus sign just for convenience. Once we have R11, we just divide by it, and that guarantees that Q1 is a unit vector. So that's all Q1 is. It's just a normalized A1. So we're just normalizing the first column of A. All right, but either choice plus or minus would give us a valid Q1, and that it's a unit vector. We're just choosing a plus sign as a convention. Well, I need to make a note here again. Okay. Now, all right, so we have a first column of Q1, and we have a first column of R1. Then what? Okay. So now, if I look at the second column of A, if we go back here for a second, the second column is the matrix equation. Well, the left side, the second column is just A2. On this side, the second column of this equation would be the columns of Q1 times the elements of a second column of R1. So it'd be Q1 R12 plus Q2 R22. And that's what I have here. I'm going to make that a little bigger just so it's easier to see. Okay. And that's all we get because the second column of R1, being upper triangular, will only have these 2 non-zero entries. Now, at this point, we already know what Q1 is. So we just need to solve for everything else. We need R12, we need R22, and then ultimately we'll get Q2. So we want to make sure that Q1 and Q2 are orthogonal. and that Q1 and Q2 are also unit vectors. So in fact, Q1 and Q2 are orthonormal. So, okay, I'm going to add an intermediate step in here. Okay, so if I take the inner product or dot product of both sides of this equation with Q1, okay, so I need all this. Okay. Okay. Now, if I require that the Q's form an orthonormal set, then this equation right here is going to simplify quite a bit. Because inner product of Q1 with itself is 1. Q1 is designed to be a unit vector. So I'll just fill in 1 for that. And then Q1 and Q2 is not known yet, but what we do know is that Q1 transpose Q2 must be 0 because they're supposed to be orthogonal to each other. All right, so right side, it simplifies to R12, and that's what gives me this formula right here. So now, in this whole equation, what is known and what is unknown? This is given. This is now known once we do this. Now, what about this? We need to make sure that Q2 is a unit vector. So what I do is go ahead and compute. I'm basically going to isolate this term. Q2 gives a direction. R22 gives a magnitude. So I go ahead and take the norm after moving this to the other side. That gives me the magnitude. So then I just divide by that magnitude and I have Q2. So any questions about what happened here to make sure that Q1 and Q2 are orthonormal and that this is satisfied? So now we can keep going. So in general, each column of A is equal to this linear combination of the first k columns of Q or Q1. And these coefficients in a linear combination would be corresponding elements in column K of R1. So to compute these coefficients, I just take these inner products, just like what was done here. So that applies in general. Then, once I have these coefficients, I subtract off the contributions from earlier columns of Q1. So now what I have is RKK times QK. I take the magnitude to figure out what RKK is. And then I just divide QK. So I compute the columns of Q1 one at a time. And in the process, compute the elements of column K of R1. And that's the whole process. Once I go up to n, k equals n, then I've orthogonalized all the columns of A, and I have all the columns of Q1. And that's the whole algorithm, which I will show now. Okay. Okay. Okay, so here we have it. So we're going to iterate over all the columns of A. I set V to be the jth column at the start. And then what I do is I figure out the contributions of all prior columns of Q to this column of A. That gives you these coefficients. So then I subtract off those contributions here. And once I've subtracted off those prior contributions, I have my new column of Q, but it has to be normalized. So I compute its magnitude first and then divide by it. It gives me my new column of Q or Q1. And that's it. That's the whole process. So that's Gram-Schmidt, as you may have been taught in linear algebra. Any questions up to this point? Okay. So now that we've seen the algorithm, I can tell you what's wrong with it. What they don't tell you in a linear algebra class, it's numerically unstable. And to give you an idea as to why, as an example, suppose that A1 and A2 are nearly parallel. So we're almost linearly dependent. Then what happens is, when I compute this, that was done up here to get my my new column of Q, a second column, this is almost zero. And because we're subtracting two terms that are not necessarily small, but the result of subtraction gives us something that's nearly zero. That's called catastrophic cancellation. So there's a lot of round-off error in this result. So therefore, since this is inaccurate, Q2 is going to be inaccurate, and it's just going to contaminate the whole process from there. So this is what results from computing these coefficients actually in this manner and updating what was supposed to be my new column of Q and subtracting off these terms. So I'm going to show you a slight, it's going to turn out to be very slight modification of this algorithm. It's called modified Gram-Schmidt that is that somewhat at least helps deal with this problem. Okay. Okay. So modified Gram-Schmidt. Okay. So I'm going to use outer products to explain how modified Gram-Schmidt works. Okay. So here's a factorization we're trying to get. And now, instead of expressing R in terms of its columns, I'm expressing in terms of its rows. So R1 would be a full row. R2 would have 0 as the first element, and so on. And then this is only going to have one non-zero element at the very end. So when I write Q1 and R1 in this manner, that means I can express A as a sum of outer products. And we've seen this kind of representation before with Cholesky. So it's good to keep in mind. So I can write Q1 R1 as this sum of outer products. So now, if I take a first column of both sides of this equation like I did before, then this is what we get. And we go ahead and compute Q1 like before. So that part is no different. Okay. But then, here's where things change. So before I move to compute Q2, what I do is I compute inner product of both sides of this equation of Q1. And what I do is I look at that column by column. So if I take Q1 transpose column J, that's going to give me R1J. So this is an element in the first row of R1, column J. Now, this is the exact same formula as in classical Gram-Schmidt, but what I do now is I change A by subtracting off all the contributions of Q1 to later columns of A. So here we have this sum of outer products, but now I'm leaving out the first one because I'm getting it out of the picture. So then what happens is I will continue to compute Q2, Q3, etc., but working with this modified A instead of the original A. So now I look at the second column of this matrix equation. And what that'll give me is second column of A, this modified A, is a multiple of Q2. Because what I've done is in this update here, the first column, the first row and column are gone. All of these deal with rows and columns 2 to the end. So now I have this, which is the same kind of equation as this one for a first column. So now I can go ahead and compute Q2. And if you compare the computation of R11 and Q1 to R22 and Q2, you see they're very similar. So here this works with the original first column of A. This works with the second column of a modified A. And then we keep going. So, so I compute the rest of the second row of R1 by taking these inner products of Q2 with each remaining column of the modified A. So then I would then subtract off the contributions of Q2 from A2 to get A3 and work with A3 to get Q3 and so on. Now, if you forget about floating point arithmetic, the formulas you get for Q1 and R1 are exactly the same as in classical Gram-Schmidt. It's just that now we're computing things in a different order than before. So classical Gram-Schmidt computes R1 column by column. Modified Gram-Schmidt effectively computes R1 row by row. Okay. Now, to give you ideas as to why computing elements in a different order should even matter, I'm going to use a simpler abstract example. Suppose I'm computing these two inner products, U transpose V, U transpose V plus W. And U transpose W happens to be 0. So these are equal. But what if this expression that I'm trying to compute happens to be very small compared to W? And what that means is, since the result of this should be nearly 0, what's going to happen, but none of these items are negligibly small, then what's going to happen is I'm going to be computing a small number from adding or subtracting larger ones that will cancel out to give me something that's nearly 0, or that's much smaller than before. So what will happen is we have a risk of catastrophic cancellation from this vector being present. So if we were to get rid of this, if we have this vector v plus w and we subtract off the w, then we just go ahead and compute U transpose V, which would be a much safer operation than the original. So it's very important to avoid computing small numbers from adding and subtracting larger ones. That's how catastrophic cancellation occurs. Now, the funny thing about modified Gram-Schmidt, though, is, well, I could describe an algorithm that's going to carry out exactly this. Like we go ahead and keep updating A. It turns out that all I really have to do is take the algorithm I showed you previously for classical Gram-Schmidt and make a very small change to it. So I'm just going to make a copy of that and show you what the change is. Okay, so let's make sure I have all the text updated here. Dang it. Okay. Now, all I have to do in here to change this algorithm so that from classical Gram-Schmidt to modified Gram-Schmidt is a surprisingly trivial change considering what I just described. That's it. That's the change. I'll include what was there before. Qi transpose AJ. Because in classical Gram-Schmidt, we're taking these inner products with the original jth column of A. But the thing is, V is set to that jth column, and then what happens down here is we subtract off all contributions to that jth column from previous Qs. Then then that's what I take the inner product with. So if I'm computing an element of R that's in row I, that element's being computed after Qi has been subtracted off. So the reason why these are equivalent is, what if I subtracted off from V just to get to this point? I've subtracted off contributions from prior Qs, which are already known to be orthogonal to Qi. So that's why whatever I subtracted off from V would contribute nothing to Rij anyway. So that's how you can see how it's at least mathematically equivalent. But the reason why this works from a numerical stability point of view is, let's suppose the columns of A are almost linearly independent. So what's happening is V, by the time it's all said and done, might be pretty close to 0. But at least we're arriving at that by subtracting smaller and smaller things. And Rij will be more accurate. It's not as contaminated by round-off error. Therefore, this is not as contaminated by round-off error either. Okay. So we're limiting the accumulation of round-off error in Rij. So even though this is not perfect, because this vector V, if columns of A are nearly linearly independent, might be close to 0. At least there's less round-off error to contaminate that result. And so at least it's a very small change to the kind of Gram-Schmidt you're taught linear algebra classes. That it's still, while not as good as householder givens, at least it's viable. Whereas classical Gram-Schmidt, definitely not in a computational setting. So to give some concrete results about accuracy, so the Q1 is computed. So Q1 hat is the actual computed Q with floating point error taken into account. Now Q1 transpose Q1 is supposed to be identity. So because of round-off error, it's not going to be exact, but U is machine precision. So in most systems, it's generally around like 10 to the minus 16th times the condition number of A. Now, so if A is ill conditioned, like if it's columns, if A is nearly singular, then this error could still be very large. By comparison, the Q1 that you get from householder reflections does not involve a condition number. It's just proportional to U. So it's still much more accurate. It's just that this is for modified Gram-Schmidt. For classical Gram-Schmidt, this would be even worse. As far as efficiency is concerned, here's how many floating point operations are needed. This is for householder QR, but if you just want to compute R, so you're basically applying householder reflections to A to make it upper triangular. This is how many operations it would take. And then if you want to explicitly compute the thin or economy size QR factorization, it would take this many more operations, so the same number of operations again, by applying those householder reflections to identity, at least the first n of them, to get the first n columns of Q, which is Q1. All right. Okay. So if you keep in mind is, okay, householder much more numerically stable than Gram-Schmidt, modified or not. But if you just want a thin Qr factorization with Q1 in explicit form, then that's a little less costly. Because notice the work for modified Gram-Schmidt is 2mn squared. Now, to get R1, householder is a little cheaper, except this gives you Q1 and R1. This gives you only R1, and you have to do that kind of work again to get Q1. So it's roughly twice as much work to get Q1 R1 explicitly with householder, but you also have this significant difference in accuracy and numerical stability. I didn't do an explicit comparison of householder and givens. Householder is a little more efficient than givens, just for a general case of computing QR factorization. And that's one reason why a lot of people still use it. It's just that for certain situations, as I mentioned, with givens, like suppose you only have a few entries to 0, or you want to do things in parallel, then givens is nice for those situations. So, so we can see that all three of these approaches have their virtues. So it just depends on the setting in which you are computing Qr factorization and what you actually need from it for whatever problem you're trying to solve. Because generally, you don't compute Qr factorization in a vacuum. You need it for something. And sometimes it calls for having an explicit version of Q or Q1, and sometimes it doesn't. So that's something to keep in mind too. Right. And so now you've seen three very different ways of computing the QR factorization. And we have plenty of time, so are there questions about this or about homework? I notice that we're still waiting for homework ones from some people. Actually, think about half of you. I want quite a bunch today. Okay, you had your chance to ask questions. Okay, well, I guess it gives me a little more time to rest up for PDEs, which I'm sure some of you could use too. Okay, I will stop recording at this point then.